All right, welcome back to Introduction to Quantum Field Theory, episode 31. That's not right. This is episode 32. So, welcome to episode 32, Spinor Fields with Yukawa Interactions. We're now going to talk about the interpretation of perturbation ansatz for spinor fields. So, just a little bit of recap so that you understand where we're coming from again. We have the inhomogeneous Dirac equation, and that is given by I gamma mu partial mu minus m c equal to the negative of the derivative with respect to the conjugate spinor of the interaction potential. And we have that the general solution for this equation with an interaction potential V is going to be C, depending on x, the integral over y of the special solution, which depends on x and y, relates the two positions, and of course, the derivative here of the interaction with respect to the field. So let's recall the perturbation ansatz. Recall the perturbation ansatz. And this is the ansatz that we did for the video on scalar fields with Yukawa interactions, where we took the scalar field and said that it is equal to the free field plus this factor G here, the coupling strength, coupling strength coefficient, and then you have phi1, G squared, phi2, and so forth. And you also have this same thing for the spinor. So you have free field spinor, G, C1 plus G squared, C2, and so forth. And recall that this is only true when you have G less than 1. And of course, the closer to 1 that G is, the more and more terms you'll have to include in this summation. Therefore, we now want to plug these into this equation and then equate different factors of G, like we have done in the past few videos. So first, let's compute what the derivative of the interaction potential is. So recall that the interaction potential is the coupling strength, and then you have the spinor product and phi. So this means that the derivative of v with respect to phi bar is going to just be g c phi. I know it must be super easy to tell what I'm saying with v, c, and phi. Okay, so we have this fact right here. And this implies that phi naught plus g, or c1 plus g squared, c2, and so forth. So now we're plugging in the perturbation ansatz and this into this equation right here. So the left-hand side here is this side. And now we have g integral d to the 4y. Shoot, why did I start t when I'm recording? Well, I'm gonna have to go do that again later. Dang it. Oops. So yeah, we then have the special solution, and then we have the terms inside of it. And I'm again only going to include the first degree term because otherwise the multiplications get too hairy, and we don't need super hairy multiplications to understand what's happening here. So we've now plugged in the perturbation. And next we will expand out this term, the right-hand side that is. So we're going to have this quantity. First, we're going to have C naught times, or phi naught. So we get C naught or times phi naught. Next, the term with only one factor of G is going to be G C1 times phi naught, and then G phi 1 times C naught. So we end up with G of C naught phi 1 plus C1 phi naught. Then for G squared, we're just going to end up with C1 phi 1 and so forth. Now, we can expand this G into this. So expanding the G inside, and get G here, G squared, and G cubed. So let's see what this means for the solutions. So now we're going to equate. So we're going to equate terms with only one G and with G squared. And we're going to put those right here. So therefore, the first one is C1, which is the integral d for y special solution. And it's just going to be C naught and then phi naught, E naught. And likewise for C2, we have this integral over y, CS, the special solution. But now we get C naught phi 1 plus C1 phi naught. And you can continue doing this. Now, let's discuss. So we solved for in the scalar fields with a Yukawa interaction. We know what C1 looks like, and we know what or we know what phi 1 looks like. So now that we know what phi 1 looks like and C1, we are now prepared to make the interaction diagrams, or yeah, that's what I'm going to call them. They're not Feynman diagrams, but they're like interaction type diagrams. So let's talk about the first one. This is for phi 1, and this is going to be like this. And I'm going to have CS. This is X. I'm going to forgo the subscripts. Just going to say X, Y, and have the 45-degree angles like this, dotted and dashed. And this is phi naught. This is C naught. So that is the interaction diagram for C1. Now let's go back to this and copy. Well, I'm going to change the style to make these dotted to be consistent with my current style. Now we have phi1 here. And I guess I used an if and only then if there, and I did a colon. So let's just make these consistent. And also, just for consistency, get rid of the news here. So now we have these two terms. We can now make C2. So we can say that C2, we can say that it corresponds like this. So we have our X, our Y, our special solution, special little boy. Oh, shoot. This actually has, notice that I accidentally skipped over key detail. Notice there are two terms here, which means that we're going to actually, okay, where's the, there we go, 45 degrees. And another 45 degrees. I have these are both representing the same position Y. And both of these represent the special solutions here. And the first one is going to be C naught and phi one. So we end up with this. We end up with this, where this is C naught. There we go. And this one right here is C or phi one. And here we have that this is C naught. And this one is phi one. Except I'm going to change something just to make it easier for our next rewrite. I'm going to change these. So we have this. But now we know what these interaction terms are now because of this. Wait, hang on. The heck? Did I do something wrong? Oh, no, I didn't. Okay. I just give me 1 second. Why am I having a stroke here? What's going on? Okay. I see what's going on. We should also change this. I just saw that I drew something slightly off in my notes, so it's messing with me. Yeah, C naught, and then this is C1. And we can say that this is the same here, so we can copy this. That's kind of satisfying to see. So we have this. I don't like how big this is. There we go. And we can actually solidify this one. Say that this is the special solution again, because we're now plugging in this C1. So now we're going to basically put this in here and say that get to this. And this. Both of these have the same dotted style. A few not. And not same dotted style. Sorry, this one is like this. We get C naught, phi naught here. And this position is a new position. We'll call it Y prime. And we can do the same thing here, where we now make this solid. And this is phi s, the special solution for phi. And it has two solutions here. Taking a lot longer to draw these than I thought it would. But that is okay. Prime. So now we can see more clearly what these interactions look like. So when you have just one term here, then when you have multiple terms, they branch off. And then when you plug in everything so you can see the base level interaction, you get this. So they're pretty, it's interesting because not even in the book that I'm teaching out of, these were, what he did is he presented two separate trees, but really they're part of the same tree. And I think it's more easy to visualize how this is counting the different possibilities of interaction. Here it's just branching out once. Here it's also just branching out once. Here it's branching out twice, but now there are also these things. So now it's branching out twice, but then twice again, and then twice again. So it's counting all the interaction possibilities.